Okay, let's go ahead and get started. I think most of you might not even know who I am, so I figured maybe I should introduce myself before I introduce the speakers. So I'm Professor Yoni Kans. I'm new faculty here. I joined in December, and I'm still back and forth a little bit between my former institution and here. But I was delighted to be able to be here today to introduce my friend and colleague, Professor Lindley Winslow. So we've worked together for, I think, almost a decade now.
No.
Yeah. In a good way. Professor Winslow got her undergrad and PhD degrees from Berkeley, was a postdoc at MIT, and was faculty at UCLA before moving back to MIT, which is where I met her when I was a graduate student there. Her original training is in neutrino physics, but for the last several years, she's been doing really amazing work in new experiments to look for axion dark matter. That's been a really wonderful collaboration between theorists and experimentalists. And I can't tell you how gratifying it is to be able to go from like idea on a blackboard, which I still remember like when that got drawn on a blackboard, to like literally an experiment you can touch and put your hands on if you're careful. You know, it's very cold, so you probably don't want to touch it when the fridge is on. I'm really delighted that you'll get to hear about all the amazing work that Lindley has been doing in this direction and going forward in the hunt for dark matter. So I'll let her take it from here.
Oh, good. Okay. So we're still like good in the back. Okay. So thank you all for having me. It was very nice that it snowed. It's just been cold in Boston, so I was enjoying the snow this morning. So what I wanted to talk to you about is wavy dark matter, and specifically axion dark matter, and my experiments, abracadabra. It's even hard for me to say it sometimes, to DMRadio. So as Yoni very nicely said, the work that I do is divided between axion dark matter and neutrinos double beta decay. The first part of my week was for the Snow Lab EAC, where we talked about double beta decay a lot. But today I wanted to tell you about axion dark matter. What combines these two topics is new physics at the gut scale, for me at the very least. But really, as an experimentalist, what combines these topics, they're both really difficult experimental problems. And so the things that my group likes to work with are photodetectors, both warm and cold, quantum dots, crystals, which are just basically big quantum dots, magnets, and dilution refrigerators. And a lot of the work is moving more and more towards these cryogenic type detectors, of which there's quite a few experts in the room. So what are the big questions that motivate these topics? Well, these are some of the biggest questions facing fundamental physics. What is the particle nature of dark matter? And why is there more matter than antimatter? So this afternoon, I wanted to talk about dark matter. And I particularly love this new image from JWST because it really actually shows you all in that picture what it is that we are trying to do as experimental and theoretical nuclear and particle physicists. You look at that, you see the stars, you see the bending of the stars due to the massive lens. And so the first thing you notice is there has to be dark matter. You're seeing that, the distortion of the light, and well, there's galaxies, and you needed the dark matter to collapse into galaxies. For the other problem that I'm looking at, then the next thing you might notice is that's all matter, and where's your antimatter? But it's all right there, and that's really the big motivation for this work, and I'm sure what motivates many people in the room. So what are we doing today? We're going to talk about the axion dark matter, but afterwards, if you want to talk about neutrinos double beta decay, I love that topic too. So for axion dark matter, I feel like I need to like preface any talk with dark matter these days is that there is some sentiment that we have this sort of zoo of dark matter. And some could say that that's sort of a bad thing. I would say that's a good thing because you go to a zoo to find animals and you will find animals at the zoo. Okay. I also have children. They've kind of outgrown Curious George at some level, but I love this picture of all the animals at the zoo with a balloon, because that's also a little bit when you're talking about the dark matter experiments, that not only are you looking for different zoo animals, each animal has a different balloon. And when we're talking about that now, with a lot of the novel detectors, that balloon is actually different types of quantum sensing. How do we push beyond not just what is a difficult detector, but actually push the bounds of quantum mechanics to pull out these very small signals? So I would argue that yes, it is a zoo, and I'm hoping in this talk to kind of explain to you why we need all these different detectors, especially within axion dark matter. but also kind of where these balloons are and why they're interesting. So goals for the top: describe the suite of experiments that are required for a definitive search for the axion. Understand how these relate to different regimes of quantum sensing, and connect these axion discovery to other key questions in particle and nuclear physicists. And then finally, tell you a little bit about what we actually do in my lab at MIT and now at Stanford. Does that sound like a good plan for this afternoon, everyone? Okay, it's a little bit for everyone. And then we can discuss my theory motivation at dinner, which I'm sure people will have some critique for. So, wave-like dark matter. So most of the dark matter you're familiar with is like a classic particle. But there is a whole zoo, once again, of candidates that count in this sort of wavy dark matter candidate. They all have masses less than 1 eV, and at this mass, this is when you're crossing the particle border. And you can categorize them by how they interact under CP, that sort of mirror symmetry that exists. So you have pseudoscalars, scalars, vectors. What connects all of these is that their cosmological history is athermal. These things were never in thermal equilibrium with the universe, and that gets us around a lot of the constraints that would come from their cosmological evolution. So that is where we're going to start. And so there's a lot of candidates over here, but one of the most famous is the QCD axion. So the QCD axion was invented to preserve CP symmetry in the strong interaction. And so once again, there is this CP, this mirror-like symmetry that we think is fundamental in particle physics, or is sometimes fundamental in particle physics. The strong interaction does not violate CP, so you had to put in something to fix it. So what that is this new one, U1 PQ symmetry, and a new particle shows up, the axion. And you can couple it to photons, you can couple it to nucleons, you can couple it to electrons, and there's broad categories of models. But what's nice about these two broad categories of models is they give us a very clear experimental target, which is this yellow band here. So this is the plot that every single axion talk has to show. Yes, I'm like, everyone has seen this maybe once if you've seen an axion talk. On this axis, you have the mass of the axion, and on this axis, the coupling to the standard model, to things that we can measure. The photon is usually what we're talking about. So GA gamma gamma, the coupling to the photon in that talk. So all experiments are going to be pushing down, and the goal will be these KSVZ and DFSZ models. And we can talk a little bit more about those later. I would also note that in addition to the QCD axion, higher order theories like to make things called axion-like particles. They don't necessarily solve the strong CP problem, but they just show up. And they would show up in our experiments, since I'm an experimentalist, kind of the same thing. They would just show up in kind of different parts of the parameter space. And I need to change the colors on this plot. But yes, they would show up anywhere kind of in this area. So if you're building a QCD axion experiment, you will run through out parameter space on the way. And that's always nice to have sort of in-between goals. So I have to warn you, though, as I talk, I don't say QCD axion and ALP every single time because that gets tiresome. So I'll just say axions and just remember that I mean both of them, and that the target really usually is these KSVZ and DFSZ theory targets. So now that I've given you the motivation, we're looking for dark matter. We have these two models that are sort of general models, the KSVZ and DFSZ models. How do you actually build a detector to go after wavy dark matter, in this case, axions? So we'll go back to those pictures of how you might think of particles. And so on the left, you have heavy dark matter. These are like the billiard balls that we think of with WIMP dark matter. And things come in, they scatter, and it's very easy to visualize. You might think, well, the axion is lighter. Maybe I can still think of it as particles. You've actually, since you've crossed this wave particle boundary, you have to start thinking them as truly as fields. And how would you actually measure a field? And to give you some numbers to put on it, if you translate masses into de Broglie wavelengths or the occupancy number, a nano EV axion has a wavelength that is on the scale of 10,000 kilometers, where if you're talking about 100 GeV WIMP, it has a wavelength of 10 to the minus 16 kilometers. So you see it right there. One is a wave, one is a particle, and they have corresponding occupancy numbers that really tell you that it's a field. Are we convinced that we're dealing with waves now? So when you start talking about detecting a wave, though, you're talking about a fundamentally different way to detect particles. These are not your classic high energy physics or nuclear physics particle detectors. You're going to have to measure a wave. So if you have an axion, the field exists and it will have a frequency proportional to the mass. So quite literally, throughout space, you have this axion field. What you're going to pick up in your detector is a wave with a very specific frequency corresponding to the mass of the axion. What's really nice is that the theoretical prediction for it is incredibly narrow, 1 part in a million. This is so narrow that it's not going to be replicated by a radio station. They're much broader. So it's a very beautiful signal to look for, but you have to start thinking in frequency space. The other nice thing about nature is that this very narrow line actually has a very distinctive shape. Due to the velocity distribution of the axions in the halo, it's going to end up with this sort of shoulder-like feature. And for those that do analysis, it's always really nice to have a distinctive feature, not just a peak in your data. So that is what we need to build a detector to measure. You might hope that there is some theoretical guidance of where in frequency space to look for the mass of the axion. There is some limits. My favorite is the limit at 10 to the minus 22 eV that just comes from a wavelength longer than the size of the galaxy. You can't be dark matter and have a wavelength longer than the size of the galaxy. I think we're okay with that, right? On the upper limit, you start hitting bounds that come from stellar cooling. The cooling of red giant stars kills a lot of particle models. And so that gives you the upper sides. Then you get 2 different cosmologies, depending on whether your QCD or your axion was made after inflation, the post-inflation scenario. After inflation, you're much more constrained by your cosmology, and that's somewhere around a micro EV and above. In the pre-inflation scenario, you have much more parameter space open, but there's still some more bounds that are coming from things like black hole superradiance that constrain us a little bit more. And for the most part, we're going to be looking from 10 to the minus 12 EV up to about 1 EV for your axion. That's still 12 orders of magnitude in mass space. So that's still not a lot of constraints. So then the question is, how do you build a detector to do that? So in so much of particle physics, we think of things like ATLAS or CMS, where you're measuring everything all the time. That's not going to work when you're measuring a wavelength. And so think about the electromagnetic spectrum. I put it up here just for fun to bring people back. Look, there's a rainbow. You wouldn't build the same detector for a radio wave as you would for a gamma ray. That would be silly, right? So when you're talking about wave like dark matter, you can't build the same detector for 10 to the minus 9 EV as you do for 1 EV. You're going to have different types of detectors. So right from the beginning, you're not talking about one experiment. You're talking about a suite of experiments. And this is what's contributing to that sort of zoo-like feel of the new dark matter experiments. It's that inherently you will need different types of detectors to go after different types of the parameter space. So it's not that we don't know what we're doing. It's just that physics does not allow us to build one detector to go after 12 orders of magnitude. It's just that simple. So now going into the actual physics of detecting it. As I mentioned before, with the axions, you have 4 different options: coupling to photons and coupling to various parts of the strong interaction via EDM, axial nuclear moments, or axion electric moments. People are actively developing experiments on these couplings. They tend to be more difficult and involve atomic physics techniques that are difficult to scale. Photons are easy to detect. So as an experimentalist, that's where we start, because this experiment is going to be hard. So you might as well start with the most straightforward thing to measure: photons. We're good with measuring photons. Okay. So that's where we'll start. And if you're measuring photons, you will notice the lovely F mu nu up here, and you're dealing with Maxwell's equations. And so these are the axion modified Maxwell's equations. And as someone who just finished teaching the first course in electricity and magnetism at MIT, this is so much fun to put up on the board as the last lecture, because you have, after your first class in E&M, seen all of these, and you can figure out what the effect of the axion will be right from the beginning. I'll note we'll neglect the terms that have to do with the gradient of the axion, and so you're just modifying Ampere's law. And so you're going to deal with Ampere's law in different regimes, wavelength regimes. And so thank you, Yoni, for the slide. So dealing with the axion in different regimes, you have the quasi-static regime where your wavelength is much, much larger than your experiment. So this is your very low mass experiments. And you end up with just a true modification of Ampere's law. These are real effective currents, if that's okay to say. In the regime where the wavelength of your axion is about the same size as your detector, you're in the cavity regime. So these are like hard junior level, easy graduate level problems to solve, but you are going to actually have to calculate modes in a cavity. The last regime is the highest mass axions, and the wavelength is much, much smaller than the size of your experiment. And this is the radiation regime. And here, these are some pretty hefty electromagnetic calculations. And I think there's still a little debate with whether they've gotten them completely right, but there are experiments that are going after these measurements. Cool. So we can walk through these regimes and kind of give you examples of the experiment. I'm going to tell you more about abracadabra. This gives you an idea of sort of what the cavity experiments are going to do. You're really building a cavity and looking for the axion interacting with it. And then the final, the radiation regime, where you're going to use a dielectric hagioscope to force the conversion. And that was just sort of a list for those that really love detectors. So then I think the question is, where are we as a field? So this is a like crazy version of that first plot that I showed you, where you have the mass of the axion in this axis and the coupling of photons here. For the most part, we have a lot of bounds that are coming from various astrophysics and cosmology. And this is what's really pushing that sort of 10 to the minus 12 to sort of 1 eV. And here is your definitive models. A couple experiments have actually pushed down and eliminated small parts of the parameter space. But for the most part, we have parameter space at the highest masses and at the lowest masses. And if you're looking at the parameter space down here, this is the parameter space that corresponds to a pre-inflation axion and a gut scale axion. And this is what I find really interesting, is to find that relic that occurred before inflation. These are the post-inflation axions, and they're very interesting themselves. But you can tell where my bias and my heart is. So that's a very busy plot. I think we can summarize it a little bit more. And so this is very much slides that are taken from the recent SNOMAS process in the US for understanding the priorities of US funding, which is fun to say today. So no experiments as of sort of 2020 had actually probed the QCD band. As of today, we have a couple experiments that are into that QCD band, but we have a lot of that space yet to search. So there was a big call in the US for these dark matter new initiatives, some of which are more particle-like dark matter, and 2 that were wavelength QCD experiments. They are DMRadio and ADMX EFR. And this leads us to kind of what the question is of how do we fill in this whole section down here. What we do know is what's going to be true of all of these sort of superconducting experiments is that you're going to need cryogenic infrastructure to cool things down to millikelvin temperatures. You're going to be using high magnetic fields to force the conversion of these axions. And you're going to need to use high Q cavities to actually enhance these signals. And finally, you're going to need some sort of beyond the standard quantum limit readout. And so this is what I was telling you is when you're making measurements of very, very small pulses in your detectors, you're actually going to want to actually push beyond the noise limits inherent to quantum mechanics. And so, as many in the room very well know, if you're trying to measure 2 variables in quantum mechanics, there are limits to what you can do. But if you only are interested in one of the variables, you can put all your uncertainty into the other one, and in that way, get beyond or go beyond the standard quantum limit of quantum mechanics. And so several experiments have done this. Haystack was the first axion experiment to actually do the so-called squeezing and reduce their noise levels below what you would predict from quantum mechanics. And there are ways to do this over the full frequency range of the axion. So from back action evasion at the lowest frequencies to Rydberg atoms and the more traditional squeezing at the highest frequencies. But when you start talking about different experiments combining different frequency regimes with different measures of ways of avoiding the standard quantum limit. Once again, this is how you end up not with a zoo, but a zoo with different balloons for each animal. And so this is at the heart of what's going on, is that you are being forced to have different experiments at different frequencies, and they have different ways of avoiding the standard quantum limit. So that was my standard quantum limit slide. I hope it had some clarity. And so that is what gets you to this sort of plot of all of the different, especially at the highest masses, axion experiments that are using slightly different geometries with slightly different beyond the standard quantum limit readout to try to get this full parameter space. And I put in blue there too that are of the going after different couplings for the axion. So that was your introduction to the overall kind of landscape of axion experiments. You have these two cosmologies. You have about 3 frequency regimes, 3 noise regimes for the beyond or standard quantum limit. And if anyone would like to make bets with me, I think it's going to take us about 5 experiments to cover this whole frequency regime and get to a definitive search. I would note that this would be very exciting to actually do these searches because they would actually tell you about other parts of cosmology and particle physics. So I like to go through the not just what could we eliminate in the parameter space, but what could we actually discover? Because in so much of my career, I have measured 0. So it's really fun to think about actually measuring something. So let's pretend that there was actually a discovery in this parameter space that you see here, right around sort of a micro-EV axion. This is an axion that was made after inflation, so we know when it showed up. It is down on the QCD line, so it's telling us something about an expanded Higgs sector, expanded quarks. It's telling us about new extensions of the standard model. You would then go ahead and do these tests to the other couplings to the standard model that I showed you later. But what was really neat is that you could look at the line shape and actually would tell you something about the distribution of dark matter in the halo, because that line shape tells you about how the axions are arranging themselves. You could see dark matter streams, etc. If you had a discovery here, this is an axion that was made before inflation. It tells you about new gut scale physics. It also would predict some sort of expanded Higgs or additional quarks. There would be possible effects on the CMB signatures that you would predict because this was a thing that existed before inflation. And then finally, the last 2 would be the same. You would then try to test it with your nuclear couplings, and you would also look at the line shape in the halo to see that it really is dark matter. So finally, the scenario that I kind of love would be a discovery of the axion somewhere up in the middle here. And so this would be an axion-like particle. So it's not these sort of more standard extensions of the standard model, but some proof of higher order theory, which would be really exciting. And in this regime, there is some possible signatures and accelerator-based experiments. And so once again, though, you would still have fun testing the couplings. In fact, testing the couplings would be even more important in this scenario, and the line shapes. And so this excitement is why there's so many people that now will want to tell you about their favorite axion experiment. So this is the number of abstracts at the US APS meeting per year. And then I point you to these 2 white papers on wave dark matter that kind of summarize where we were a year or 2 ago. So finally, that takes us through the landscape. And I'll remind you that I love that like pre-inflation axion at a nano EV. And that's what I would really like to measure. So I'd like to now move over for the rest of the talk and tell you how we're going to go about doing that. And my favorite experiment, Abracadabra, which did anyone predict was actually an acronym? Yes. So I write it on the slide to make sure that I remember it myself, but it does tell you exactly how the experiment works. So it's a broadband/resident approach to cosmic axion detection with a B field amplifying B field ring apparatus. That last A is a hard one. Okay. So a reminder, what I'm interested in is these nano EV axions that correspond to the pre-inflation scenario. And if you're in this regime, you're going after the quasi-static regime where the wavelength, you have very light axions, so the wavelength is much, much larger than your experiment. And so that is what Abracadabra was designed to do. So the big question at the heart of Abracadabra is, what is a B field ring apparatus. And so Yoni made reference to something that was sketched on my office whiteboard sometime in 2017, I believe, which was this. So it's the B field ring apparatus is a toroid magnet. In the quasi-static limit, you have this B field running around the donut, as it were, and you're going to get an effective axion current that's running around the toroid because it'll couple to the B field. You're just modifying Ampere's law. And this is the time of the talk where I force everyone to get their right hand out and go, where will a magnetic field show up? Well, you have an oscillating current. That current is oscillating with the frequency of the axion mass. And so you have an alternating B field in this direction. Right-hand rule, you'll create a real B field up to the center of the toroid where classically there should be none. And since it's like 3 o'clock, I'm not going to make everyone do the right-hand rule, but I am tempted. I'm restraining myself. Okay, so that's what we're doing. Classically, no magnetic field, and you see something there, it's an axion to first order. For those that have been looking for dark matter for a long time, this is a background-free experiment to first order. And that's what we always want in these sort of rare event searches, is to have an intrinsically background-free experiment. And so at some level, that's what really excited me to see this up on the wall. Cool. And so once again, this is the signal that we'll be looking for. There's going to be some sort of noise because you never get away from all noise in the universe. And you're looking for a very narrow peak in frequency corresponding to the mass of the axion. So what is it that we needed to get started? It was a Eager award. It's a special kind of NSF award. Just you tell them that I would like a magnet, a very cheap magnet, and they get you one. And then we already had a dilution refrigerator and a squid current sensor. And then we put it all together to try to build an experiment. So the question is, does it work? So this was the assembly of the first abracadabra toroid. We used these little Delrin pieces to make a support to wind the magnet onto. And so here is that support there. You see a little pickup ring. That ring is to pick up that induced magnetic field due to the axion, and a second ring, which is the calibration ring, to calibrate so that we know we could see an axion if there was one there. And so then you get an idea of kind of actually putting together the thing. There's a lot more epoxy in real life. And there it is installed in the late fall of 2017. I would note that it did not work the first time. And so some surgery was done, a reduction of the loop, and some more suspension to keep away from the vibrations of the dilution refrigerator. Dilution refrigerators these days are mechanically cooled. That means you're shaking the whole magnet. Any sort of fringe fields on the magnet shaking will look like an axion field, intrinsically. And so that's what we were worried about. So the whole thing now hangs from a Kevlar thread. So nothing like your thesis experiment hanging by a string, literally. So that was the running joke of the graduate student on this. And so it's hard on this projection to see it, but you can see the Kevlar string running through there, the squids at 700 millikelvin, and some copper to thermalize the whole thing. So this gets us down to actually reading out that pickup loop. You have two options when you're reading out that pickup. You could put it directly into a squid current sensor. This is a broadband approach. It allows you to see all frequencies at the same time. And that is very nice because traditional particle detectors, you measure things in energy, so you see all the energies at once. And that looks like any sort of analysis you would do at the LHC or in a dark matter experiment more generally. The other option is to couple it through an RLC circuit. This is a resonant readout. You get an enhancement of the signal due to the Q value of the resonator as you scan. And so you can get a Q value of 1,000,000. So the answer is you really would like to do a resonant approach because that gives you 1,000,000 times more sensitive experiment. But this is a lot more to engineer. And I would tell you that we were doing this on a shoestring or a Kevlar string in this case. And so for the first version, that was not possible. But this will come back in a minute. So yes, so we do the broadband readout. We can talk more about squids if you would like. And then the last thing was the Morse shielding. And so my favorite story about this is that MIT used to run a linear accelerator. It was decommissioned, and one of the jobs of the graduate student was to go harvest the mu metal shielding off the old accelerator. So your many skills that you need as an experimental graduate student. the ability to use clippers is one of them. Okay, and so that gives you the level, though, of the experiment Abracadabra was. It was a true demonstrator scale experiment, with the exception of the magnet, which was the main sort of heart of it. So those are the first results. And here is the data from this little tiny, like grapefruit size experiment. So in frequency space, remember that's where we are. And this is the power going through the pickup loop. I will notice this is, there's 1 megahertz, and so 100,000 hertz, 100 kilohertz, 10 kilohertz. At the lowest frequency, you see a bunch of lines here. Those are not axions. That is that vibrational noise I told you about. But as you see here, right around 100 kilohertz, you have this period where it's quite quiet. And the signal we're expecting is very, very narrow. Where we are, it's sort of the theoretical noise floor of the squid. And that was really exciting because that proved that this technique could actually work. And so at the highest frequencies, we start running out of our ability to shield the experiment. Once again, we clipped it off the accelerator. So we also start ending up at the bandwidth of our electronics. I would note that calibrating this detector was non-trivial. Injecting a signal here and matching up all the mutual inductances. Once again, remember your intro electricity and magnetism. So that was a lot of work, but it gets one slide. And then finally, you put it all together and you try to extract that axion signal, and this is what you get. So this is the first results of Abracadabra. At the highest frequencies here, these are the results of the sort of long-running ADMX experiment, a cavity-based search. Here is the solar axion experiment CAST. These two have been running for quite a while. And with just the little grapefruit, we were actually able to set competitive bounds within this parameter space, which was really cool. We then attempted to upgrade Abracadabra, and so the lead graduate student, Chiara, the Salemi, the junior graduate student, Callie Roy Pappas, put together a new geometry. This is cylindrical geometry to try to pull in more flux and be more sensitive. The answer is we were more sensitive. We were also more sensitive to noise. So we were no longer limited by the squid noise floor, but other environmental sources. But there was some parameter space where we finally beat that gigantic solar axion experiment. So we're pretty proud of that. So that is sort of the best in this frequency regime at this point. I need to say a big thanks to my collaborators on this, especially since one is sitting in the audience. Thanks, Yoni. But that was sort of the limits of what you could do with the size that would fit in a very sort of a standard dilution refrigerator. And so the question is, what do we need to do next to actually go after that sort of pre-inflation axion that I'd like to do? And so that brings us to the DMRadio collaboration, of which I'm the spokesperson. And what is it that we want to do? So we're going to need bigger magnets. We're going to continue to need dilution refrigerators, and we're going to need to move to this resonant readout. We continue to need some vibration and warm and cold shielding, though this time I hope we're not harvesting it off of an old accelerator. And so this is the plan. So once again, on this axis, the axion mass, on this axis, the coupled of photons. We envision this in 3 stages. So DMRadio 50 liter, which is just a scaling of Abracadabra. DMRadio meter cubed, which is sort of the next intrinsic size that you would go to. And then finally, DMRadio gut, which is really sort of more of an R&D path, but really the ultimate experiment that you would like to do. So DMRadio 50 liter is under construction. It's been the main focus of my Axion program for a while. It will try to do this ALP-like search, and it'll be a test stand for quantum readout for this frequency regime. And just to have proof that it really is coming together, experiments have these periods where you're trying to get them all ready to integrate, and then everything comes together at the same time. So here we are. The components have begun to arrive at SLAC. You see over here the 1 Kelvin shielding. I went and visited the magnet vendor a few weeks ago, and all of the parts are there. It's such a beautiful magnet. It's complicated because we are doing the resonant readout, and you actually need a slit in the magnet. And those are some very happy graduate students with our 1K plate. So then after 50 liter, we move to meter cubed. This is the DOE Dark Matter New Initiative. This is an experiment that really would like to push down to DFSZ. The problem is that you're at these higher frequencies. And so remember the different regimes where you are, in the long wavelength regime or the regime where you are basically a cavity. As you hit about 5 to 20 megahertz, you start entering the cavity regime. And so you're in this weird regime between being an effective current and actually having cavity modes show up. So a lot of the focus of DMRadio meter cubed has been actually simulating the details of the experiment and understanding basically the Jackson E&M that's going on it, and how do you actually read out this detector? And the answer is, in order to avoid the different modes in the cavity, you're actually going to need different sizes of coaxes, different sizes of cavity. And so we figured out that it's about 6 different coaxes to cavities, coaxes to fill up this regime. And so we are now sort of finalizing the design of that detector, now that we really understand this, the simulation of it, and doing very project-like things like writing TDRs and resource loaded schedules, et cetera. And so then finally, DMRadio Gut is the experiment that I would really like to build, but we need to get experience with the other 2 before we do that. So it's a long-term R&D program, both on magnet technology, because this thing is going to need to be big, and the quantum sensing that'll allow you to actually pull out this signal. So we have a paper that you can find on the archive that gives you some sort of rough parameters of what would it take to do this experiment. And so a baseline design for an experiment that's probably 15 years away, but either way, it gives you the order of magnitude of what we need to do, is something like a 16 Tesla magnet at 10 meters cubed, with sort of slightly improved quantum sensing. And so you'll have to take my word that quantum sensing parameter is just a little bit beyond what we can do now. The thing that might worry you is a 16 Tesla magnet at 10 meters cubed. Yes, that would worry people. So what I would point out is that sort of requirements is actually very similar to the magnet requirements for fusion. And so one of the big excitements of Massachusetts is Commonwealth Fusion, which is down the street from my house. And they are in the process of building a magnet with actually higher magnetic fields and just slightly smaller volume. So this magnet is about to come on shell and exist. And so the question, though, for us is, could you actually integrate that magnet with the quantum sensing? So that's the hard part. So we are continuing to sort of pursue that and try to understand what the parameters of that experiment actually would be. Also, it allowed me to talk about fusion in a particle physics talk. Okay. So then the last thing is, as you build something as large as DMRadio Gut, you would like to look for other things. And so one of the things we've been doing with Abracadabra is trying to understand what you could actually look for with an axion experiment. And so one of the things that's been put out there is that, could you look for gravitational waves? So these are high frequency gravitational waves, not the LIGO gravitational waves, but they might be coming from, like, say, in-spiral primordial black holes. And so we actually set up an experiment. So here's a theory paper telling us that maybe it could work. And here are the simulations of what the signal would look like. What's really cool about it is, on the top, you see kind of an axion signal. It's very symmetric. The gravitational wave signal is actually it's asymmetric. And so you would have a slightly different pickup, or you're looking for a slightly different, you would try a slightly different geometry of your pickup within your sort of magnet setup. So what we proved is that we could run both the axion experiment and the gravitational wave search at the same time. Callie Roy graduated this summer, and we're finishing up that paper now. So that's the goal: build a fusion magnet with quantum sensing, look for nano EV axions, pre-inflation axions, and maybe some high frequency gravitational waves. And in that way, go from Abracadabra and a sketch on the board through DMRadio 50 liter, DMRadio meter cubed, straight through to the gut scale experiment. And so with that, I hope I convinced you why everyone is excited about axions. Hope I convinced you that there's a reason for the zoo and the animals with their balloons, and that you might have a couple questions for me. So thank you.